Yes? Okay. They asked me to talk in English. Today we have Peter Hammersley. I don't know how many of you know Peter Hammersley. Peter Hammersley has been at the IAC for a number of years now, right?
1990.
99? And he came from Imperial College, where he worked a lot with Mike Selby, the late Mike Selby. And he's been involved in many of the instrumentation projects at the IAC. And now, I don't think I would exaggerate if I say that he's the soul of the GTC. If the GTC succeeds for any reason, it's because of him.
If it exists, that's a good question. Okay. We thought, okay, first of all, I'm going to speak in English. I do apologize. One of the reasons is I know some people in Florida are also interested in hearing the talk. And so that kind of makes it difficult to do it in Spanish. The reason to give this talk now is also because since the first CAT round, where we will offer the GTC, starts, or it has a deadline for the proposals of the 3rd of October, then it makes sense to have a talk to describe exactly where we are with the telescope and what we're expecting to do in the next few months, so that you can have some idea of what to expect. So what I'm going to talk about here is, first of all, we'll do an introduction to the observatory. What is a GTC? I mean, many of you already know that. And then basically break it down from first light right through to preparing for day one into kind of what have we been doing in each stage. And so there have been stages where we've been observing. So, for example, June, July of when we did first light. It was about 2-3 weeks when we were observing. Then we've done 3 months between March and July of this year. And then in a couple of weeks' time, we'll start observing again. And then we'll continue observing right the way through to March. And then we'll start with the science proposals after March. Okay, so what is a GTC? Well, this is a picture of the observatory. Basically, there are 3 main sections. We have the dome, where the telescope sits. We then have the annex building. This building actually has 2 parts. On the part on the left, we have all the offices. So that's where the control room is. We have the office, we have the kitchen, we have the television. So all that part is in the air-conditioned part. It also has the humidity is stabilized. It's actually quite pleasant working there. In the part on the right is where we have the workshops and the air conditioning systems. So, for example, we have all the air conditioning for the dome is all controlled from the annex building. If I can persuade this thing to work. There we go. And there's a large plant here, also the oil pumping system. The idea of putting it in a building separate from the dome is because all these large pieces of equipment cause vibration. We don't want that vibration going up onto the telescope, because if the telescope starts to shake, then our image quality dies immediately. The final building is the auxiliary building. Here we have things like the generator, the transformers. This is equipment that produces a lot of heat. Now there's also a thing here that you can't see, and that there's a tunnel that actually goes under the dome, under the annex building, to the auxiliary building, and then comes out from a vent about here. The idea of that is we can suck all the hot air out of the telescope and from the air conditioning plants, and we can pump it out at about 100, 150 meters from where the telescope is. That means that all this hot air goes downstream. And so hopefully that doesn't come up and affect us. At least when the winds are from the normal direction, which is from the north, all that warm air is blown away from us. And so that again improves the observing conditions. And so an awful lot of work has been done to make sure we have very, very good image quality. The telescope itself, it's actually very difficult to get a good picture of the telescope because it's so big. It fills the dome completely, and it's almost impossible to get a very, very good picture. And so this is a fisheye view. If you want a better idea and you can't go to the telescope, on the GTC web page it's called a panoramic cam, something like that, where it's a little flash program that you can actually move around the telescope and you get a far better idea of what it looks like. The telescope itself weighs about 400 tons. So that's the moving mass. The tube, which is this part here, weighs about 75 tons. So that's the amount of mass, the amount of inertia that we're moving about. And so we have very, very powerful motors to do that. The telescope also has Naismith platforms, which are here and on the other side. Here is where we can mount the big instruments. They can weigh up to about 10 tons. On Cassegrain, which is at the bottom of the telescope, we can mount instruments that weigh up to about 2.5 tons. And then right at the back, where you can just see the holes in the tube, if I can point to them, here you go. These are called bent casts. These can take far smaller instruments, weighing about a ton and a bit, but not much more than that. Because these are actually directly mounted onto the tube, and so they'll put a lot of weight into the system. Huh? Who's pinched the pictures? And here you go. Okay. Okay, the heart of the telescope is the primary mirror, M1. And this is a view of a segment. So each segment is about 1.8 meters across. It's actually about 1.84 meters across. They weigh about 500 kilograms, and there are 36 of these segments within the mirror, within the whole of M1. The segments themselves are about 8 centimeters thick. And if you have a mirror that's 1.8 meters across and only 8 centimeters thick, that is not thick enough to support its own weight. What that means is if we were to move that around the sky, as it stands, the whole mirror will deform. And so we lose image quality. Therefore, below the mirror, we have what are called whiffle trees. These are basically a series of balances that distribute the weight evenly across 36 points behind the mirror. So instead of supporting it on just 3 points, we're actually supporting the mirror on 36 points. These systems can also... Oops. Oh, wrong way. Okay. We also have some motors behind these levers, so we can actually put a force into the mirror. That means we can actually change the shape of the mirror slightly. So each segment we can control the shape to remove focus and astigmatism. Then this whole system is supported on 3 actuators. And it's these 3 actuators that kind of allow the segment to move relative to the overall mirror cell, which is at the bottom here. And so these give us 3 degrees of freedom, tip, tilt, and piston, and it means we can individually move each segment. The big trick of M1, and it's why lots of engineers have spent an awful lot of time trying to get this to work, is that we have to align these 36 segments with an error in the end, particularly when we mount Canariacam, of about 50 nanometers. Or if you like, a rotational error of about 25 milliarc seconds of that order. You have a mirror that's weighing about 16 tons on top of a tube that weighs about 75 tons. And really, all the work we've been doing, a large part of the work, is to make sure that we can do that with the necessary accuracy to provide good image quality. If we don't do that, again, the image quality dies, and we don't meet our specifications, and we don't get good science. And that's what counts in the end. The other crucial mirror is M2, the secondary mirror. The secondary mirror itself is here. It's a piece of beryllium. It weighs about 45 kilograms. That's because we have to do chopping for the mid-infrared and also fast tip tilt. What that means is we have to move the mirror up to 10 times a second for distances that are quite large, particularly when chopping. And so if the mirror weighed too much, that would be impossible. So this is a piece of beryllium. It's been light-weighted, so the overall mass is about 45 kilograms. A solid piece of glass this size, this is 1.2 meters, would weigh what? It would be about half a ton again. So again, we've had to put a lot of work in this. And this is actually the most difficult mirror to polish. It was a problem getting the blank in the first place. They had, 4 attempts before they finally got it right. And then polishing it out. Because this mirror is also optimized for the infrared, so it's slightly undersized. And so you can see it has this serrated edge. And it's been polished out right to the edge of the mirror. And that is extremely complicated. Because when they have the polishing tools, what tends to happen is they go over the edge, and so they put a lot more force into the edge itself. And you get what's called downturn, so you lose the image quality at that point. And so what they had to do was, they had to take a lot of care, and it took them quite a long time also to work out how to do it, to polish this mirror right the way out to the edge. You can also see we have a central hole. Again, this is because this mirror is optimized for the infrared, so that it will be very good for EMIR and for Canariacam. The idea is that we can take all the baffles out. The secondary mirror baffle you can't see on this image. We're just about to mount it. And so we have two options. We can work with the full optical baffles in place, which is what we use for Osiris, or with the baffles out. There's a direct view from the focal plane right through to the sky for something like 10% larger than the mirror. So the only thing that you see from the telescope focal plane is mirror. You can see a little bit of the spiders, and then everything else is clear. It's clear to the air. And that's because in the mid-infrared, the sky is a lot darker than a baffle. A baffle you see perfectly. You put your hand in front of a mid-infrared detector, it saturates immediately. The sky, because it's a lot cooler, is a lot darker. And so what you want to see around the secondary mirror in the mid-infrared is just pure sky. And so that's what we've done. This mirror also has 6 degrees of freedom that we can move for keeping the telescope aligned. It's on a hexapod system, so we can move the mirror in tip tilt, X, Y, Z for focus, and also in rotation, but we don't use the rotation because it's not necessary. The reason for that is this whole mass up here is about 2 tons. The primary mirror weighs 16 tons. The whole cell is 75 tons. As that moves around the sky, everything moves. And so, for example, the distance between the secondary and the primary mirror changes by over a millimeter. And therefore, we have to correct that in real time as the telescope points. Also, the whole mirror sags as well slightly. And again, we have to drive the secondary back to hold so that we're in the correct alignment. Otherwise, we lose image quality again. And so this is the reason why we have this complex drive system. This is a slow drive system. You can't see it. There's a second drive system for doing the chopping, which is a fast drive system. And that allows us to move the mirror at very high frequencies. The instrument that we've been using for all the commissioning to date is the acquisition and guide system. The whole system is about, to give you an idea of the size, this is about 2 meters. It's about 2 meters in diameter. And there are 2 arms, and the arms can move in rotation, and then the whole table can move around in a circle. And in this way, we can point the arms to any position within the focal plane. Now, within the 2 arms, in arm 1, we have what's called the acquisition and slow guide camera. This is just a simple camera. It has a 1K CCD, a field of view of just over 60 arc seconds. And that is the main instrument that we've been using. The other instrument is the high-resolution wavefront sensor. And that allows us to measure exactly the shape of the primary mirror. Not only the whole primary mirror, but also what exactly the shape is of each segment. So we can put something like 16 points onto each segment. It also has what's called the phasing. This allows us to adjust the height of the 2 segments so that 2 segments are exactly the right height to within this 50 nanometers. And it has special lenslets that are adapted for doing those measurements. On the second arm, we have the fast guide camera, and it's called the segment tilt sensor. This is actually just a low-resolution wavefront sensor. The fast guide camera has a far, far smaller field of view. It's only 12 arc seconds. But we can read it out at about 150 frames a second. So with that, it will be used principally for fast guiding. Fast guiding is when we're using the secondary mirror to correct the pointing of the telescope. And that gets rid of image shake. Oops, sorry. Going the wrong way again. But also it's very, very useful at the moment for measuring what sort of vibrations we have in the system. And this camera only has the one detector. So we either have it as a camera or we have it as a low-resolution wavefront sensor. Low resolution is something like 18 points over the whole mirror. And again, this is useful for measuring the alignment of the system. And so these are the instruments that we've been using to date for commissioning. And these form the bulk of... basically, all the measurements that we'll use to commission the telescope is based on what we'll get off those sensors. Okay, so now we come to the first set of observations, which is first light. This was a very trying time. I think I can speak that for all the people from Grantecan there, because we had a very, very strict deadline. Now, we did first light with only 12 segments. The reason for that was, if you put in full 36 segments, you end up with 36 points. The whole focal plane looks a total mess. we have to control those points by hand to begin with. And if you've got 36, it takes a lot longer than with 12. And so using 12 segments at the beginning basically gave us a problem that we could manage. We could manage M1, and we could start working out the routines for keeping the telescope aligned. We also didn't have tracking at first light. We could point the telescope, but we couldn't track. So that meant that basically we had to work near Polaris, because that's the only thing where the source would not depart very, very quickly from the field of view. And we were primarily using the acquisition and slow guy camera. However, for the very, very first light, and you can actually see it on this picture, we had a very high-tech, here it is, wide-field camera, known as a piece of tracing paper. The problem is that the first time you point the telescope, you haven't got a clue where you're going to point, because there are errors in the 0 points of the two encoders. The encoders are very precise, but there's an error in the 0 point. It actually turned out, in azimuth, the 0 point was 2 degrees off, was actually slightly over 2 degrees off, and it actually took us quite a while, it was about 2 or 3 hours to find Polaris, because it was far further off than we were expecting. The point being that a third magnitude star, you actually can see quite nicely on this piece of paper. You see the points. So each segment, you can see it quite nicely on there, and you can then move the segment, and you can actually see those points moving. The other problem we had was that, again, the first time we pointed this to the mirror and we actually got Polaris in, then the segments are all over the place, because they're just in with their mechanical tolerances, which is about 20 arc-minutes, which is basically the whole field of view that we've got. So again, if you're trying to do that on the acquisition and slow guy camera, what happens is, we'd still be trying to, A, find Polaris, because with a 1 minute field of view to get it, you will never find it. And then even when you find Polaris, then to find all the segments, which are spread over, they were about 15 arc-minutes, again, would take an awful long time. By having this piece of paper, Javier Castro, who's responsible for the optics, went up there, worked out where the segments are, then called down that he wanted a particular segment moved by so far, and then we'd move it from the control room, and then you can see how that segment, or how the point moved. And so what he did was basically got all the sources to cluster together to within about 5 centimeters. 5 centimeters is 1 arc-minute, and that is the field of view of the acquisition and slow guy camera. And so once we'd done that, once we'd pulled all the segments together, we then transfer that to the acquisition and slow guy camera, and we could go to the wall of the control room. And so this is actually, here you can see Antonio and Carlos, the two support astronomers on duty, and this is actually the very first time we pointed at a star with the acquisition and slow guy. This is Polaris. This is the first time we actually got a star that we meant it to point at within the camera. And so this is, if you like, the real first light. You can see it looks a mess. And it looks a mess because, again, the segments aren't stacked. So all the segments are pointing in a slightly different position. But that was a very useful moment. A very important moment in the life of the telescope. And then basically what we did for the next 2 or 3 weeks up until we had the full first light ceremony was we learned how to control the mirrors. So one of the tricks we did for first light is we actually spelt out GTC by changing the pointing slightly of each segment. So this is actually 3 separate images that are joined together to form the G, the T, and the C. And these are the 12 segments. And like I say, we can actually point each segment to exactly where we want. Again, another pattern that we did. This is not Polaris. This is now another star that's actually closer to the pole, so it even moves more slowly than Polaris, is we form patterns. Again, you form a pattern, you know where you put each segment, you then measure where each segment appears, and then based on that you can calculate the error in the position. And with that you can then stack the segments. And finally we did a few images of, well, this is a couple of interacting galaxies to prove that we could do some pretty pictures. And that was basically all that we did for first light. So we could prove we could take a picture, but remember, this is done without tracking. And so basically we took a series of 1 second exposures and then had to shift them back to form the image. And then between July and March, we then shut down. We stopped observing. One of the most important things that we had to do was to get the tracking to work. Now the problem wasn't as much in the code to calculate exactly where you have to point that we had. It was the interaction with the max. What you have to remember is we have a 400-ton telescope. It can move at 2.2 degrees per second, which is very fast for something that large. If we get it wrong, it can go smashing into the end stops and do a tremendous amount of damage, and that would put us back months. And therefore, the control group had to take a lot of care to make sure the system worked and worked safely. And that took a long time, longer than we were hoping. But the point was we had to be safe because, again, we actually had an accident just before first light where the dome went into the elevation end stop. There was a bug, it went into the end stop. Fortunately, it didn't cause much damage. We were quite lucky. If it had gone a bit further, it would have caused a significant amount of damage. And like I say, you've got large moving masses with large inertia. And so you have to be extremely careful when you're doing that testing. You can't just write a program and test it on a telescope the next day. You've got to go through a series of testing just to make sure the whole system is safe. Again, that takes time. It's light, I'm afraid. But again, you don't want to rush these things. Otherwise, you make a mistake, and you'll suddenly find yourself, you've got 6 months more work to do. When we restarted in March, we'd mounted 12 more segments, so we had 24 segments. Mounting the segments is actually a big job, because when you mount the segment, you've got to, first of all, illuminize the segment. You then got to mount all the sensors, all the cabling. There's goodness knows how much cabling behind that mirror. It's a whole maze of cables and pipes and goodness knows what to make that mirror work. And that, again, takes quite a long time. It's not a trivial task. And the other thing that we wanted to do was to improve the reliability of various other subsystems. So when we started in March, between March and July, we had a series of tasks. One was optical quality. This is one of the main tasks we had to do. Prove that we could manage M1 correctly, or M1, and also that we could do the alignment. Now, the way that we were working was we would put a pattern onto the mirror. So we'd open up M1 so that each segment pointed in a slightly different position. And then we'd do exactly the inverse pattern. And so, let's see if I can get this to work. So, if I can get this pointer to work. Okay, this segment here is actually that segment there. And so what you do, you put this pattern. You then measure where the points are. You know what the pattern you put is. You then invert it. You then remeasure where all the patterns are. And then you work out from that exactly what the error in the stack is. What's the error in the 0 point that you assume? Then you can apply that error, and you get a stacked image, which is what we've got here. What we found was that we were typically getting images, or stacked images, down to about 0.6, 0.7 arc seconds. We were routinely below 0.8. The other thing that we found was we were routinely as good as the DIM SIG monitor, RoboDIM. When that was operating, we were routinely getting images as good as the SIG monitor was saying that we should get. The other task that we had to do was maintain the alignment as the telescope moves. Because as I said earlier, this distance between the primary and secondary mirror will change by about 1 millimeter. And so what we did was we basically had to repeat the alignment procedure at various elevations. And then from that, calculate how the secondary mirror was moving. So we could then program that to move in reverse. And this is the OLACO, the Open Loop Active Optics, that does that. And basically, we built this model so that we could keep everything aligned. Another problem is just a simple alignment of M1, M2. If you have a Ritchie-Chrétien and M2 is misaligned with M1, you get coma. If you have a segmented mirror, what happens is you get coma in the whole image, but for each segment, what you find is you start to get astigmatism. And to begin with, we had a lot of astigmatism in the images of each individual segment. And like I said, we corrected it down to a certain level. But again, you can see some of these images here, some of these segments, have a slight amount of astigmatism. You can see it. So we know the alignment isn't perfect. It's good enough to give us 0.6 arc seconds, so we're quite happy. But we now know that during the next 6 months, we've got to improve that. We also mounted, for one night, FastCam at the request of Rafa. And we did some tests, and these images are courtesy of the FastCam team. So basically what we did was we opened up the mirror, so each segment produced its own image. And they looked at binary stars. And when I say this was a very preliminary test, the telescope really wasn't ready for doing this. And so they did some tests with separations of just over an arc second. And then you take all the images that you took and then restack them to give you an overall stacked image. And also they did some tests with images or with sources down to about 0.2 arc seconds in separation. And you can see, you can resolve it. At 0.2, we are resolving it using FastCam. Now, FastCam is an instrument that takes about 30 frames a second. It takes images very quickly, and then it has software to pick out the best seeing. So this is not what you would get on a long-term image. But like I say, what it is saying is that the segments in general are performing well. Like I say, we know we have to touch some of the segments because they're not quite perfect, but in general, the segments are performing well, and we do get good image quality of it. So we've proved that, like I say, the optics of the telescope is working very well, and we're actually getting very, very good seeing. That's as good as anywhere on the site. We also had to do a lot of work in pointing and tracking. So this is an example of a pointing model. Here's the example of the pointing model that we did in June. We did about 40 stars. And the radius of this circle here is 0.9 arc seconds. The radius of that is 2. And so you can see that even at this early stage, we're getting pointing at 1 arc second. And that's as good as virtually any telescope in the world. I know of no other telescope in the world that is routinely pointing at that level. Again, we've still got work to do. But, like I say, it's very, very optimistic. And sorry? Yeah, this is the full pointing model over the whole sky. Well, from about 85 degrees down to 25 degrees in elevation. We've also did tracking tests where we follow stars. We just let the telescope track. Very, very useful when there was important basketball games. Because it was during the finals of the NBA. And so since this was basically a 2 or 3 hour test, it was very, very useful to program them at those points. And basically, you just let the telescope track with a star centered in the nominal position, and you see how it drifts. And we're getting tracking errors of typically about 0.25 arc seconds in 10 minutes, which again is actually below specifications. So it was basically at specifications. Again, there's stuff that we've got to do. We also did some tests at high frequency. This is with the FastSky camera. And this is for a single segment. So we opened up the mirror, isolated the image from a single segment, and then took images at 120 frames a second. Because what we're interested in is what's vibrating in the system. Now, the good thing to notice here is that at low frequencies, this is basically 1/f noise. We're not seeing anything below about 7 hertz. This means we're seeing very, very low wind bounce. The wind is not shaking the telescope at all. Well, I can't say at all, but it's kind of below 0.1 arc seconds. Now, that should be compared with, say, VLT or Gemini. They have terrible wind shake, and if they don't have the fast guiding working, they can't get good image quality. And so GTC is actually extremely stable against wind, which, again, is a very, very promising result. Now, we can see some frequencies here. There's a frequency here at about 20 hertz. Again, I mean, it looks quite large. This is very, very high Q. What that means is that there's actually not much amplitude there. And this is because of the telescope. So then, these frequencies here, these is actually the segment vibrating on its mount. And again, if you work out how much it's vibrating, in this case, it's about 10 milliarc seconds. So it's actually very, very small. And there's a frequency out of about 40 hertz as well, that we can see. And this is a whole. So these are basically tip-tilt vibrations, and this is the whole mirror going up and down. We were expecting those vibrations, and it's nice that we can see them. But the vibrations that we're seeing, like I say, are at a very, very low level, which again is very good. So it means that all this work we put in to make sure the telescope was clean has worked. We also did a lot of tests on just the A&G camera itself. So this is, what is the photometry system, what is the ghosts, windowing, etc. Because again, the A&G cameras these are sensors that we have to calibrate. We have to get them to work properly. And this is a typical image that we get out. This is an image of the galactic plane that we did. It's actually near the end of the bar, if I remember correctly. The first thing to note is that when you get a saturated source, or a source that's very bright, you don't get the traditional cross, because we have 6 spiders. So you get a hexagon. And also, if you go out into the wings of the image, again, you get this hexagonal effect. That's expected. If you take the form of the telescope and then you analyze it and see what you expect, this is exactly what you expect. So there's nothing to be surprised at. But it does mean that you don't get any nice HST crosses. But again, this system is basically working. And of course, we have to take some pretty pictures. Pretty pictures are a very, very important part of commissioning. So the only problem is, of course, that, again, we have a maximum field of view of about 1/2 minute. When they mount a Cirrus, our Cirrus is going to have a field of view about 60 times larger. So they'll be able to do some really impressive pictures. But even so, for 1/2 minute, we're getting some very nice pictures. In this picture, for example, we've got full width half maxima. This was a 5-minute integration. We've got full width half maxima at 0.6 arc seconds. And this is in 3 bands. This is a detail of the Einstein cross. And so that from there to there is about 2 arc seconds. Some nice pictures of the Stefan Quartet and also Night Edge on Galaxy. Again, these aren't the famous galaxies because we can't do them. They're far too big for the sensor. So like I say, when we get a Cirrus, then the whirlpool and such like, I'm sure will be included. At the request of the coordinator of research, we did some planetary nebula. And so these are some nice pictures of planetary nebula, again with good seeing. Like I say, over the summer we had a lot of nights with seeing at around 0.8 to 0.6 arc seconds. And like I say, the telescope really was performing well in those conditions. Something slightly nearer to home, okay, that's Saturn, which you've probably guessed. And then this is the moon, photographed with my Nikon digital camera, projected onto the piece of paper. And I have to say, this is the most impressive sight that I've seen so far, because the piece of paper is nearly 1 meter across. And you get a picture of the moon that is 1 meter across, with resolution at about 1 millimeter. And you can also start to see colours and such like. And it's like I say, when you get it focused on a night with good seeing, then that is really impressive. Particularly when you stop the telescope and then the moon drifts through, because it's then like you're kind of flying over the surface. Like I say, that would be the problem when we mount the instruments. We can no longer see those pictures. But like I say, that's just to prove that our wide field camera does actually work. Okay, so between July and October, we stopped down, or we stopped again, mainly because we had to complete the mirror. And as I said before, putting in the segments is not a trivial job, because you have to put the segments in, then you have to get the control systems to work, etc. And in the end, that takes about 2 or 3 months. We also have to get the instrument rotators operational. To date, we've been working without the rotation of the field. And of course, when we mount our Cirrus, we need that capability to be there. And so, like I say, the rotators are now operational, and the moment we restart, we'll start on that. And also, we had to recoat the secondary mirror. On the first time we coated the secondary mirror, there was a small problem with with one of the corners, and so they decided to recoat it so that it is correct. And so that brings us up to where we are now. And so now we're looking to the future. And the expectation is we're going to start observing it again in about 2 weeks, with the first week being to get back to where we were, and then to start to bring online the new capabilities. So the first thing we have to do is work with the instrument rotator. We then have to work with the ANG arms off axis, because when we're doing the guiding, obviously we can't have the arm right in the field of view, otherwise it blocks the image going through to a Cirrus. And so we have to program all that, and we have to test it that we can actually guide correctly off axis. And that's the other thing we've got to do, is we've got to start the guiding. The final thing we've got to do that's really important for the commissioning of the telescope is start the wavefront sensing. We hoped to actually start that over the summer, but we couldn't because there was a misalignment problem. We know what it is, we're going to correct it. The wavefront sensor, what it gives us is far more information about how the telescope is aligned, what the segments are doing, than we were able to get using the methods of destacking M1. And so that will allow us to correct the aberrations we still have, and so it will give us a far better image quality. And then the final thing that we're going to do is we have to commission the first science instrument, which is expected to be mounted towards the end of this year, and that's a Cirrus. And then we have to commission that so that we're ready to do the science, which is, of course, what we are all aiming at. Now, like I said, the deadline for the CAP proposals is, I believe, the 3rd of October. We will start the observations in March. It is expected that about 50% of the time that we will use will be given over to science. And 50% of the time will be commissioning. Now, basically, when we get to March, we'll still have a number of issues with the telescope to sort out. We have to then mount the second A&G system, the acquisition and guide system, on the other Naismith focus. We have to commission that. We then have to mount CanaryCam and commission CanaryCam. And so, like I said, there's an awful lot of commissioning work that has to go on, that will be going on through next year, probably well into 2010. Because the commissioning of a large, complex system like this, you don't do overnight. It can be about 5 years before everything is finally working properly. But like I say, by the beginning of March, we are expecting that we will have the telescope and the instrument in a condition that we can offer very high quality science in certain modes. So we're only going to offer some certain modes that we're relatively confident we can commission, which is the broadband imaging, the tunable filter imaging, and long slit spectroscopy. The modes like the multi-slit spectroscopy and the more complex charge shuffling modes will take longer to commission. And so, since we're very restricted on time, we're going to concentrate on what we consider to be the priority modes. And the final point is that, well, we're asking for proposals of about 10 hours in length minimum. Again, if we got flooded with a lot of proposals for 1 or 2 hours, that will cause a massive overhead for the support astronomers. And we're going to be in a conflict once we get to March, because we either commission the telescope or we support the community, the observations of the community. And again, a lot of small proposals would just take too long. And so the conclusions. Well, the image quality that we're getting off the telescope is very, very good. It's actually far better than we're expecting at this stage. Because we very quick, I mean, even by first light, we were getting down to 0.6 arcseconds after about 3 weeks. And like I say, we've been routinely at that sort of level all through this summer. And telescopes like the Keck took a lot longer to get there, to get to that sort of level. And this will get a lot better once we start to get the wavefront sensor working. The pointing and tracking is also working extremely well. The telescope is actually behaving itself extremely well, far better than we were actually expecting. And so now we then have the next tasks of, well, basically it's field rotation, guiding, and the first science instrument. And then, of course, we get into the interesting part of the first science. And that's it.
Okay, so there's time for questions. The aula is overcrowded, so you have to pass the microphone when you have questions.
Okay, Peter, you haven't spoke about the time for sign verification. What are the plans for the sign verification? Because a few months ago you made a call for proposals, and
am I allowed to transfer that to Hammersley? But basically, we can't do the science verification until we've got the instrument commissioned. But then, now part of the science verification is part of the instrument team's problem. But we also have to do, and before we can go to the community and start doing full TAC proposals, we have to run through some proposals where we know that there's a chance of a whole lot going wrong. Because once you get to TAC time, you're guaranteeing almost that you will do the observation and you do it correctly. And there's a lot of interaction between the telescope and the users that we have to sort out. And so that's when we'll start to do the time. And so I'm guessing that will be into February, January, February, depending on how the commissioning of Osiris goes, but it will be around then.
And what about the site verification proposals of CanaryCam?
Again, once we get CanaryCam mounted, that will be next summer. I mean, we can't do them before we mount it to the instrument. And so, like I said, we have this. One of the main reasons for the science verification proposals is that we've got to debug the interface between the observatory and the users. And it's easy to do that with a small number of people who realize the situation that we're in than once you get into the TAC. Once you get into the TAC time, then you have a huge number of proposals. And so, like I say, with the CanaryCam time, again, I'm guessing this has to be decided, but again, we'll do the SV during part of the commissioning of CanaryCam. And that will be when we mount that, which is currently planned in the summer. Is that right?
More questions?
So at the beginning of the talk, you said that as you move the telescope to different positions, the distance between the primary and the secondary changes by 1 millimeter.
That's right.
So
that's the tube.
Okay. So how does that actually translate into the quality of the image in terms of?
Basically, the focus moves in the focal plane 100 times more than the distance between the primary and the secondary. And so basically you end up with a 10 centimeter defocus. So the focus position of the telescope is now 10 centimeters away from where the focus is of the instrument.
But does it affect your seeing?
Well, I mean, the main one is focus. You also have the fact that, yes, the secondary moves. That introduces coma. Okay, and that's why we have to drive it out. But 10 centimeters, let's work it out. That will give you an image that's about 5 millimeters across. 5 millimeters is about 3-4 arcseconds. So you see it. So if we did nothing, going from the zenith to the horizon, if we're focused in the zenith, then by the time we got down to about 25 degrees, 30 degrees, we'd have images that were about 3 arcseconds across.
Okay, I have, well, first, just to give you congratulations to you on all the team who's working on GTC, because it's evident that those who will not work in this place cannot really appreciate the lot of efforts that are going behind that. But I have two questions. One first is, if you had to give from what you've learned in your work in these years for the telescope, if you had to take one thing to teach to the people who are doing or aiming at doing the ELT, what would it be? And the second is, what would you bet will be a first for the IAC? A first paper in GTC or the first meal in the new cafeteria?
Okay. What takes the time is these are huge, complex systems, and systematically you underestimate how complex these systems are. I mean, for example, the integration tasks, Javier Pancorbo, who's done a very, very good job in controlling all that, he has something like 1,000 tasks all written out. I mean, if he was to print it out, it would be over 1,000 pages. And you have to manage all those tasks, and bring them all in at the right time. And it is complexity. I mean, you look behind M1, you see the complexity there immediately. It is quite horrendous. And it is managing that complexity that takes the time. And that takes a lot longer than you expect. And as for the bar, well, we've been waiting for that for how long?
Can you repeat or list the top a few problems you are facing right now in order to actually to make your telescope ready for the first light?
Okay.
First question.
Okay.
And the second, well, just for us, I don't know, a few things which makes the different GTC from the keck. It will be interesting also to hear from you. Yeah, because as I understand, it was the next generation, even though it based slightly on design of keck.
Oh, yeah. Okay, what do we have to do? Well, like I said, we have 4 large tasks, that we have to do before we're ready to mount our series. That is, one, put the wavefront sensor into operation, because that's what will give us better image quality. I mean, the image quality is acceptable now to start commissioning, but not for starting science. We have to get the image derotator working. There's a lot of stuff, you know, when you go off axis and you have to calculate how everything moves around the focal plane. All that work is done, we've got to commission that. The third point is the A and G arms. So these are the arms of the A and G. Again, we have to program those so they can pick up stars. We can tell the telescope is pointing here, and we can then identify we have a star at a certain position, and the arms then point to it, we can grab that star, and then the fourth thing is guiding. We have to get the guiding working. And like I say, this is foreseen that we will at least do the hard part, or the initial stages, very, very soon on all those areas. And the second question, sorry, my memory's going. Oh, that's right. What is the difference? Like I say, the idea is based on the keck. The technology is very different. So the M1, okay, we have segmented mirrors. The mirrors are actually different from the keck mirrors. The keck mirrors are 7 centimeters, these are 8 centimeters. And there's a whole series of things, when you actually look at it, The engineers we haven't just taken the Keck design and made a few modifications. No, the engineers have started from scratch. They've used that as a guide, but they've started from scratch. So the positions are different. The frequency that we can control M1 is different. At the moment, we're controlling it between 10 and 20 hertz. So basically, we're measuring the position of all the segments 10 and 20 times a second, and then updating the position is to hold the mirror correct. The Keck does that at about 1 to 2 hertz. And like I say, in the end, it's actually expected to go faster than that, up to about 50 hertz. Also, under the mirrors, we have motors to change the shape of the segments. So what we can do is we can do a measurement on what is the actual shape of the segment. We can then correct that in real time. And then measure it again. The Keck have to do a measurement. The next day, somebody has to crawl up onto the telescope and start playing about with thumb screws to change the forces. Then they measure it the next day, so they haven't got that immediate feedback. That gives us the advantage, actually, that if we find deformations and we're expecting a certain level of deformation between the horizon and the zenith, as we point the telescope, then we can correct that in real time. So we can actually build that into the model. So the telescope, the quality of the optics will be better. And our mirrors are actually better than the Keck. They were done in a different way, and our mirrors are better quality than the Keck. Oh, sorry, if I can come back to the previous question, what was the most difficult thing? The most difficult thing has actually been the dome. And it's all true in virtually every telescope. The engineers massively underestimate the complications of the dome, because they think, oh, it's a chateau and such like. We've still got problems with the dome. We can only open the dome, so we've got a viewing angle clear onto the sky of about 75 degrees at the moment. We cannot open it the whole way. And that's because the gear, the motor in the gear system isn't powerful enough. When it goes all the way back, there's just too much force. And like I said, the problem is, the engineers when they were building it, it wasn't the Grantecan engineers, we knew the problem. But particularly the people who were building it were not used to building large-scale structures with very high precision. And so, I mean, for example, the rails, when we looked at the rails, they were something like 3 or 4 centimeters off, way bigger than the tolerances where they should have been. And so we've had to do an awful lot of work to correct these defects so we can operate the dome safely. And like I said, at the moment, we can only open the dome so we have a clear view onto the sky of about 75 degrees. So if you want to do photometry, we can do that at the moment between about 75 degrees and about 25 degrees. If you're not that bothered, and if you go to about 80 degrees, for example, which is the limit of many of the Altaz telescopes, then you will lose about 2% of the light, so it's not a big loss. If you go right away to the zenith, you'll lose half the light. But like I say, there is this issue. And it's because domes are systematically underestimated for their complexity. Sorry.
My question is about a thing that is very important for planetary science. I know that the telescope is prepared since the beginning. I think it's in the beginning to track and guide a moving object. Yeah. But you didn't mention that. Okay, and I worry about the fact that if it is possible to do it, or it would be, and when.
Okay, currently that has not been implemented and not tested, because like I say, we've been dealing with primarily the optics, trying to get the optics to work well and the basic pointing and tracking. When would I expect it to be done? I expect it to be done March, April time, to be honest. Because that's when we'll have the engineers to put time in. We know exactly how to do it, it's planned. But like I say, we have to implement it. And that depends on engineering stuff, and that's limited.
Do you have any plans to make any commissioning data publicly available to help preparation of proposals in March, for instance?
We hadn't thought of that specifically, but I'm not quite certain what sort of data you would want.
Any new telescope, I mean, produces new data and is very useful for the users, I mean, to know the real capabilities of the instruments, not just on paper, but looking at the data and working on the data. Just commissioning data.
No, it's something I have to admit I had never thought of. I don't know.
We're not looking at any special effects on the stars.
Yeah, but that's enough for many purposes. I mean, to
That's something you haven't thought. We could think about it.
I'm talking about Osiris data.
Cyrus, you'll have to ask us. Yeah.
And then, as soon as the instrument is working, we start with the science verification proposal, and then we run immediately into the semester.
I have a question. You mentioned that for the next semester, 50% of the time will be dedicated to science.
Yep.
Can you say how many nights will go to open cut time?
Good question. Specifically, no, at the moment. However, you can do the estimations. So 50% of the nights, there are about 183 nights in the semester. So that means about 90 odd. You then have to top slice the guaranteed time for a series, which is about 20 nights. That gives you 70. The big unknown at the moment is the ESO time, because that comes out of the Spanish time. And so that is the big unknown that I haven't got a clue what the answer is. I don't know.
The order of 80 nights for the Spanish community.
Okay, so more questions? So we thank Peter again for his talk.